Welcome to AP Pre-Calc Lesson 4.2. This is day 1, talking about parametric functions and how we can model planar motion using parametric equations. We want to understand that the graph of a parametric function can model particle motion in the plane. In our first lesson, we found some techniques we could use, and in this lesson, we're going to use practical life experiences related to parametric equations. So in this first example, let's consider that we have a sailboat moving with an eastward velocity of 8 kilometers per hour and a northward velocity of 1 3/4 kilometers per hour. You can see that rate of change here, eastward 8 and northward 1 3/4. At time 0, the boat is located at the point -2415, where the distances are in kilometers from the port. Our port is back here at the origin. So if we let t equal the hours as our parameter, we can write a set of equations that would model this behavior. So x in terms of t would be -24, that's where we're starting at x, plus our rate of change at 8 kilometers per hour. And then our y of t would be 15, that's the y coordinate, plus 1 3/4 in terms of time. In part B, we want to find the time when the sailboat is located 25 kilometers north of the port. So north 25, we want to set our y coordinate 15 plus 1 3/4 t, set that equal to 25. Subtracting 10 from both sides, then 1 3/4, subtracting 15 from both sides gives us 1 3/4 t equals 10. And dividing on our calculator, we're going to have about 5.714 hours before the boat is 25 kilometers north of the port. How far east or west from the port will the sailboat be at this time? And we want to justify it. So figuring that out with x is 10 over 1 3/4. We have -24 plus 8 times 10 over 1 3/4. The x of that time, which was about 5.714, is 21.712 kilometers. That's east of the port because it's in a positive direction, east of the port. Part D, at what time will the sailboat be due north of the port? Well, due north of the port is when x is 0, and then we could solve that for the value for y. So setting that up, the x of t has to be 0, and 8t minus 24 is 0 when t is 3. So in 3 hours, the sailboat is due north of the port. And then finally, part E, how far from the port is the sailboat at this time? Show your work that explains your answer. So at that time, the y of 3 hours is 15 plus 1.75 times 3. So the y of 3 is 20.25 kilometers. So that ordered pair is when x is 0, y is 20.25. That's the location at 3 hours. Moving on to example 2, we're going to use time as a parameter. And we're going to call this curvilinear motion. When we're using parametric equations, not only can you find the location of an object with the x, y coordinates, but you can also know at what specific time the object actually reached that location. This is called projectile motion. We're going to use these two general equations. X of t is the velocity times cosine of t, and y of t is going to be that parabolic shape, negative 1/2 g t squared, where g is the gravity, and v sub naught sine of theta times t plus the initial height. Let's make a note of this. It's really important to understand that this whole paragraph here, where t is given the time, g is the constant acceleration due to gravity. So we're getting into the physics world here, and h is the initial height of the object. Depending on the units that are given in our real life application, we're going to either use 32 feet per second when the units are in feet, or if we're given metrics, we're going to use the gravitational constant, 9.8 meters per second per second. The equation for x gives the horizontal distance, and the equation for y gives the vertical distance. So let's jump into one of my favorite sports, baseball. Suppose we hit a baseball with an initial velocity of 150 feet per second at an angle of pi over 4 radians, which is 45 degrees. Making contact 3 feet above the ground. So we're going to set up the parametric equations that are going to model the path of the baseball. Now you can either use radians or degrees. It just depends on your teacher's preference. So the x equation would be 150 cosine pi over 4 times time, and the y equation would be negative 16, because they gave us feet. We're going to use the gravitational constant, negative 1/2 32 t squared, and so on. So half of 32 is 16, and it's negative because we've got that upside down behavior going on. T squared plus initial velocity 150 times the sine of pi over 4, all of that times time, and the initial contact height of 3. So we had all of those things going in our equation to set up the model for the parametric or projectile motion. Now, for part B, we're going to use those equations. We want to know where is the ball after 3 seconds and explain what you know. So after 3 seconds, this would be great for your calculator. The x of 3, we're going to plug in a 3 here, and I'm getting 318.198. And then the y of 3, you've got to plug in a 3 here, square it, that's 9. Plug in a 3 here after you carefully multiply. And my results are 177.198. So what does that mean? Can you think that through? So after 3 seconds, the ball is about 318 feet away from the batter's box, because that's the horizontal distance from the batter's box. And it's also 177 feet roughly above the ground. So it went 318 feet out and 177 feet up. G-R, I can't spell and talk at the same time. G-R-O-U-N-D. How long is the ball in the air for part C? So just like any quadratic word problem, we want to take negative 16 t squared plus 150 times the cosine of pi over 4, that's square root of 2 over 2, t plus 3. We want that to equal 0. Now think about this from a graphic point of view. If I take my calculator out and graph that equation, negative 16 t squared plus 150 radical 2 over 2 t plus 3, and I graph that in terms of x. In other words, I'm putting in my equation, I'm putting t as an x here, and I'm putting t squared as an x in the calculator, because I want this x, y to be this graph right here. And then I want to find when it hits the ground. So t has to be 0. I'm looking for this time over here. When does it hit the ground? And that happens at t is about 6.6579 seconds. So it takes that long in the air and then it hits the ground. Then at what 2 times is the ball 100 feet above the ground? So if we graphed y equals 100 for our second equation, there's 2 times when the ball hits the ground, because we already know it was way up there in the air at 177 feet from part B. So I want to know this time x sub 1 and this time x sub 2. So we want to know those times. And we can use our calculator for that as well, the intersection point. So if you use the intersection feature, or if you use the graph solver feature, you can do 150 square root of 2 over 2 t plus 3. The first time, t sub 1, is about 1.10 seconds. And the second time is about 5.53 seconds. So 2 different times that ball is 100 feet above the ground. And then let's look at the last example, 3. Jamie used a potato cannon to launch a potato straight up from a height of 5 feet with an initial velocity of 80 feet per second. So we're using the equation with the gravitational constant 32 feet per second. So if we use x as t, then the y of t equation is negative 16 t squared, and velocity is 80 t plus 5. Now you might be wondering, why didn't we put the cosine in here and the sine in here? Well, if you think about the idea that the potato is going straight up, the cosine of 0 is 1, so 1 times t is going to still be t. And the sine of straight up, well, sine at straight up is pi over 2. So 80 times the sine of pi over 2 is just 80 times 1. Now let's use parametric mode to graph the height against the time. So go grab your calculator and give that a shot while I sketch the picture on the grid at the right. I made my x-axis be in terms of time and seconds. I set my window on the height to be in feet, and I went up 120 since we knew we were 80 feet per second. It had to go up pretty high. So how high is the ball after 4 seconds? We want to know what's the height here at 4 seconds. So substituting into this equation, our height, y of 4 is negative 16 times 16 plus 80 times 4, that's 320 plus 5. So 256 negative plus 320 plus 5 gives us 69 feet above the ground at 4 seconds. So we know the ordered pair is 469. Part D, it's not a ball. I missed this typo here. It should be the potato. Cut and paste. What's the maximum height of the potato? Because we're shooting a potato out of a potato cannon. How many seconds does it take for the potato to reach its maximum height? Well, think about this. You know that from quadratics, the maximum or the vertex can be found by opposite b over 2a. So if we did that calculation, t is the opposite of b divided by 2a. The opposite of b is negative 80. A is negative 16. So at 2.5 seconds, this is at 2.5 seconds, we're going to get a maximum height. What's that maximum height there? So when t is 2.5, we can have negative 16 times 2.5 squared plus 80 times 2.5 plus 5. So negative 100 plus 200 plus 5. We have a maximum height of that potato out of the potato cannon of 105 feet at 2.5 seconds. The potato reaches a maximum of 105 feet. That's the end of Lesson 2, Day 1 on planar motion, parametric functions, and some modeling. See you tomorrow.